All right, ready? So 1.8, we're dealing with different kinds of numbers we work with. So far, remember, you guys have looked at, let's see, we did add, subtract, multiply, and divide, right? We did this sort of the four operations we normally do with any kind of numbers. And now we're going to look at the type of numbers we deal with. So we're going to break down each of those types of numbers. 1.9, then that wonderful section called fractions is going to come up. And we're going to review fractions just a little bit. People's favorites? No? Okay. So let's go for it here. So first of all, we got to deal with the real numbers, we call them. All this real numbers are the numbers we normally work with. There is one more set, something called the complex numbers, and those are mostly used for electrical engineering. So it's almost like that's sort of like out here in space. The numbers we normally work with are something called counting numbers. Okay. When we start counting, we normally start with 1, right? No point in counting if there's 0. And then we have something called whole numbers, which includes the 0 this time. Integers. Integers are negative and positive counting numbers. And we talked about something called debt, right? We need that little minus sign in front of numbers. Okay, and then rational numbers, that's the name we call fractions. And then we have this called irrational numbers, and we'll take a look at those as well. But anyways, those all make up the real number system. So let's go through each of these one by one. So as we look at a number line usually has integers on it. And that's the way we sort of set up a number line. So 0 goes here, anything in the positive direction goes to the right, anything negative direction goes to the left. So let's do this. Let's go through each of the definitions of the numbers, and then we'll do some exercises with them, okay? And you guys have those on your matched problems already as well. So counting numbers here. Again, it's just numbers 1, 2, 3, the numbers we normally count with. And there's a whole history behind numbers. Just sort of quickly here, as we look at history of, anthropology, or history as we think about how things developed, it seems like counting numbers developed first because we needed to count stuff. Even there's some civilizations where they're rural civilizations, they still count, and they really only need counting numbers. And they use their fingers and hands, and that's all they really need. Or if they have like sheep, they take a sheep out of the fold, and they'll have this little rock that they put into a bucket saying there's one sheep that's out there. And that's the way they sort of keep count of how many sheep are inside and outside. That's kind of sort of cool to see. And then we developed this concept of 0, and the concept of 0 developed in 3 different continents all at the same time, which is kind of weird, like whoa, because we needed to figure out a way to say, here's the distinction, see if this makes sense to you. Let's say you have a group of hunters, John and Mike. John went out to hunt and he didn't get anything, and Mike was sick at home. Should there be a distinction there? John is just not a good hunter, right? We good? He went there, but he didn't accomplish anything. As opposed to Mike just couldn't go in the first place. So it's almost like that kind of idea to, like, we have to make a distinction here, whether it should be a 0 or that he didn't do anything at all. And so we developed the whole concept of 0. And then the negative numbers seems to us, it comes from a little country, modern day Turkey, but back then it was called Lydia. It's got a cool name, a whole country named Lydia. But the king there decided, you know what, forget this barter system, like 2 pigs equals a chicken, forget it. He goes, what I'm going to do is I'm going to develop a coin system. Well, if you have a coin system, you got to say, this person owes me $5 or I have $5, right? There's that distinction to be made. So because of that, we developed sort of the negative numbers to show debt and to show you have. Okay, and then so from here, I think we're at this point here. So which of the following set are not counting numbers? That's the one we want to do. See, those of you that did not print out your matched problems, you got to write out the problem, then you got to write out the answer. It's just no fun. It's so much easier just to print out all the matched problems, and that's it. Okay, the way the book sets it up is the negative. Can you think about what the negative is here? Or the opposite here? So which ones are not counting numbers? Remember, counting numbers are anything we count with. Start counting with 1, then we go to 2, then we go to 3. So what do you guys say? -5, counting or no?
No.
Nah.
And then 1/3.
Cool. How about the 0? Is 0 part of counting numbers? Oh, no. Remember, counting numbers start off with 1 and go up. The whole numbers start off with 0 and go up. Cool. So 0 is part of the list. It's not a counting number. 1/3? Not a counting number. How about 2? Yeah, that's a counting number. 3.5? Nah, 3.5. Not a counting number. And 6 would be. So there it is. The answer to this not counting numbers would be -5, 0, 1/3, and 3.5. All right, good, good. Next one on the list here. Which of the following are not integers? Cool. All right, let's go for it. Integers, not integers, sorry. -4, that's an integer, right? That's the whole numbers, negative and positive. -2.5 is not an integer. -2 is an integer, that's fine. 0 is an integer. 3/4 would not be an integer. 3 is an integer, and then 4.7, no. So anything that's a fraction or a decimal, not going to be an integer. Okay, at this point, let's go a little bit further than what the textbook does. Notice I said anytime there's a fraction or a decimal, that's considered not an integer. Well, it's always in terms of lowest terms. Remember on Tuesday I said whenever we deal with fractions, we always got to put them into lowest terms. All right, so if you have something like this, 15/3, even though that looks like a fraction, technically it's just still 5, right, in lowest terms. So even if you see 15/3, that's still considered an integer. In fact, this is actually considered a counting number, right? Because in its reduced simplest form, it just means 5. Cool. So always in reduced simplest form. That's what you're looking at. Simplest form. All right, so now let's look at the definition of fractions, and this one's a little bit complicated. Let's sort of think through this here. And I just kind of wrote all that up there just for us to sort of think through here. So a rational number is a set of numbers commonly called fractions. And what it really means is two integers being divided. That's what this little division marker here. And then also says that b cannot be equal to 0. So you can't have a 0 in the bottom of a fraction. We know that already from like 3rd grade. But let's kind of think about this here. So when we talk about fractions, we really are thinking about decimals Remember, because decimals and fractions, they're the same. They're just a different form. So whenever I see something like 3/10, isn't that really the same thing as this part right here? That's 3/10 right here. So whenever we, again, this is a very sort of layman's definition of rational numbers. What we say with rational numbers are any decimals that stop or terminate, or they just start repeating themselves. Because any fractions that stop, we can always make into a fraction. I'm sorry, any decimals that stop, we can always make into fractions. Any decimals that start repeating themselves, we can make into fractions. So let's go back over here. So if I have 0.3, that technically means 3/10. Good. If I have this one, 0.61, that means I have 61/100. We good? So those, when they stop, it's so easy to change into fractions. Okay. Then there's these guys here. Remember this little bar line on top? It just means it repeats itself, right? This is 3, 3, 3, 3, 3 forever. So whenever a decimal is repeating itself, you don't need to know what it equals to, but there's a whole process involved, how you make a repeating decimal into a fraction. But understand, if you have a decimal that's repeating itself, it can be turned into a fraction. Cool. So 0.6 repeating itself forever can be changed into a fraction. So any decimal that repeats itself can be changed into a fraction. And because it can be changed into a fraction, therefore it's a rational number. Okay, good there? Maybe. Okay. Okay, the fun part here. So, again, we're still thinking about real numbers here. So now tell me, or show us, why each of these is, in fact, a rational number. So the question is -2 a rational number? No. So let me say it another way here. Can we make -2 into a fraction? Hey, that's right, huh? Whenever we have a -2, whenever we have any kind of number, any kind of integer value, or a whole number value, I know I can always put a little 1 underneath, right? So technically, -2 is also a rational number. Okay, how about -3/4? Is that a rational number?
Yes.
Yeah, because it's already a fraction, it's good to go, right? Cool, how about 0.666 repeating forever?
Yes.
Yes, and here you can actually just say because it repeats. You can actually even say that. If you want to know what the fraction equivalent is, you can say it's 2/3. But you can also just say because it's repeating decimal. And that's fine. Okay, and 3.5? Yeah. 3.5 is actually 3.5, right? And then we want to get it back to the definition of rational number, which is one integer over another integer, right? And then we know this. What we do is we multiply 3 by 2 is 6. We add one more to it. How about 7/2? Is that good? So I've proved it to be a rational number because it fits the definition of a number over another number. Okay, so how does this stack up? It's kind of weird. If you think about -2, -2 is not a counting number. -2 is not a whole number. -2 is an integer, right? And then also -2 is a fraction, because we can make all integers into fractions. So it's kind of, think of it, sort of just kind of bubbles up. Is that right? Kind of goes from one side, goes up to the next one. So how about how about 5? The number 5. 5 is 5 a counting number? Yeah. Is 5 a whole number?
Yes.
Is 5 a integer?
Yes.
Is 5 a fraction? Okay, so tell me if you guys agree here. So does that mean all counting numbers are going to be whole numbers?
No.
So real quick here, these are counting numbers, and these are whole numbers. So are all counting numbers also going to be whole numbers?
Yes.
Oh, I
Yeah,
think
because
yes.
we add an extra 0 to make it whole numbers, right? Are all whole numbers going to also be integers?
Yeah.
Absolutely, because once you get to this little 0 here, go like this, right? And are all integers fractions? Yes. Except for that little 0 there, right? But all integers, technically, you can make them into fractions. Sorry. Misspoke here. That little 0 could be a 0 over 1, and that technically is still a fraction, right? So all integers will become fractions. Okay, so we have this little hierarchy. Don't need to really copy it down. I just kind of got it from the internet. Actually, no, this one's be a better choice here. So, natural numbers or counting numbers. And this one I did not take from the book. I took this from another source. I think the previous textbooks we have. So just for us to understand here, all natural numbers are also going to be whole numbers. We good? All whole numbers are going to be integers, and all integers will also be rational numbers. Good there? It gives the examples of each. Okay, now let's take a look at these irrational numbers. What in the world are these? Square root 2, got pi, negative root 3, 1 plus root 5. What in the world is that? And so here's our definition. Again, if you're following me on the textbook here, we're on page 68, if you want to just follow along. Cool. All right, so irrational numbers, what in the world are those? So those are any non-rational numbers, you can say. Anything that's not rational is also irrational. That's it. So you bounce from one world to the next here. Or you could say they are non-repeating, non-terminating decimals. So they don't repeat themselves and they don't stop. So what are these kind of numbers? So I can actually make a decimal number non-repeating. If I put 0.01, put 001, 0001, there's a pattern here, right? But it's not a repeating pattern. We're good there? Kind of like 3, 3, 3, 3, 3, 3. Or 5, 4, 5, 4, 5, 4, 5, 4. That's a repeating pattern. Okay, pi is called an irrational number because if you try to get the decimal answer to pi, it's going to be 3.14159, blah, blah, blah. So notice the digits sometimes repeat. There's a 5 here, there's a 5 here. Right, but then there's no 9 over here. It doesn't repeat itself as far as a repeating pattern. Good there. So pi is considered an irrational number. Any kind of square root is also considered an irrational number because once you get the decimal approximation to square root of 2, again, this whole concept of there's no pattern that repeats itself ever. So what do we think about irrational numbers? We think of irrational numbers technically as either pi or any kind of square root that does not reduce to a whole number. We're good? Let's see. And that's really, in a sense, if you think about it, that is all the different types of numbers we use. We're good? Let's see if we are counting something, we use 1, 2, 3, 4, 5. The funny thing is, you know, when statistics come out and it says the average family has 2.5 kids, that doesn't make sense. You can't have 2.5 kids. The stats should say the average family has either 2 or 3 children, right? Because you can't have half a child. So that technically should be under a counting number, right? If you think about it. Whenever you're dealing with the bank goes into irrational numbers, right? You're dealing with irrational numbers because now you're looking at decimals that stop, right? They stop at a certain penny. They don't go on and on and on, right? So they're a terminating decimal technically. So whenever you're dealing with any kind of money, you're dealing with really with the irrational numbers. All right, so let's go for it here. So that's another thing from pre-algebra we had to deal with here. Got one more concept, actually 2 more concepts from pre-algebra still to go. You guys remember something called prime numbers a long time ago? Okay. And then something called factoring. Factoring is you just get out the factors of what numbers multiply to give you that number. Okay, and then I'm going to put an extra slide into here as well. So let's go for it. So this is from your textbook, just a quick example here. The number 12 can be factored into 4 times 3. And then this 4 is not a prime number because it can still break down to something else. And that 4 can break down to 2 and 2. And so the way we write a prime factors of 12 would be 2 to the second times 3. And so what we've done is we've factored 12 into its prime factors. We'll get into factoring later on in chapter 5, and it's going to be chapter 6, and it's going to be a lot more complicated because it has x's in it, but we're still doing the same thing. Okay, so prime numbers, there's a list of prime numbers just in case you want to see them. That is on page 69, just so you know. As you get bigger, it gets a little more complicated, like 37. Like, yeah, 37 is a prime number. It does not break down into other factors except for 1 and 37. Okay, and the other thing that I think the book sort of skipped on because it just thought like you assume it's true is this one here. It's this whole concept of divisibility rules, and I took this from the old high school textbook I used to teach from. I put the copyright law over there, so we're good to go. I cited the source. No plagiarism here. But let's go for it. Just real quick here, let's think about divisibility rules because this helps so much in math. So everybody okay with 2 though? The way you know 2 goes into a number is because the last digit is either a 0, 2, 4, 6, or 8. Good there? And there's an example where it is true, and then there's an example where it's not true. And again, doing this because last semester that's what students got stuck on. Like, oh, I wish you would divisibility rules. I think we should cover those. Okay, how do you know a number is divisible by 3? How do you know 3 goes into a number? This is kind of cool. If you add up all the digits, that number will be divisible by 3. So if you go like this, what's 3 plus 1 plus 5? 9. Does 3 go into 9? Yes, that means I know that 3 will go into 315. Cool? Here, let's add up 1, 3, and 9. What does that add up to? 13. Does 3 go into 13? No, that means 3 is not going to go into 139. Cool. All right, how do you know something 4 goes into something? Well, now we look at the last 2 digits now. So going over here, 8,512. Would 4 go into that number?
Yes.
Absolutely, because 4 goes into 12. This one, I don't think so, because 4 doesn't go into 18. Okay, 5 is easy. We know that one, right? Ends in a 0 and 5. Don't need to cover that. Number 6, because it's really a multiple of 2 and 3. 2 and 3 have to both be divisible into it. So that's kind of like both rules at the same time. So it has to be even number because of the 2. Even number because of that. And then if you add up the digits, it will still be divisible by 3. So if we go 4 plus 8, 12, 3 goes into 12, we're good. That means 6 goes into 48. 2 plus 0, it's an even number, that's cool, so 2 goes into it, but 2 plus 0 is 2, 3 doesn't go into 2, so therefore 6 won't go into 20. Cool. Okay, number 9, the sum of the digits. This is kind of like the rule for 3, except it has to be divisible by 9 this time. So 7 plus 1 plus 1. 9, and 9 will go into 9. Perfect. So that means I know 9 is going to go into 711. Cool. How about this? 9 plus 3. That's 12. 9 is not going to go into that. We're good. But this, it will be divisible by 3 though, right? Because 3 goes into 12. Okay, and the last one, number 10, is the easiest one here. The last digit is 0. That means you're good to go. 10 will go into that number easily. Okay, we're good there. Let's see. The example problems I'm going to give you, they're pretty easy to break down. The class homework and the online homework, they give you some like humongously big numbers because they really want you to sort of play with the whole concept of, is it really going to divide into it or not? Yeah, sure. I won't even call it lazy or anything. Just kidding. We're good? Okay, so let's go. Can you factor 48 into its prime numbers? Of course, start off with an easy problem. And again, if you have some confidence to work ahead of me, go for it. That's no problem. All right, here we go. Here's what I got here. So 48 breaks down into 6 times 8. And again, doesn't matter which way you broke it down. It could have been 2 and 24, that's fine. But you just keep on breaking it down. So 6 is 2 times 3, 8 is 2 times 4, and then 2 is a prime number, 3 is a prime number, but that 4 can still go down to a little bit further. So hopefully, in whatever order you have this, you should have 4 2s and a 3. Okay, how do we write it? Here it is. We're going to collect all these guys here. So 2 times 2 times 2 times 2 is really 2 to the 4th times 3 is our final answer. All right, a little bit more complicated. Let's pass that test. How about this one? 490. And so think about divisibility rules here. All right, I'm going to start it as well here. Most of you guys are done here. So what I looked at that 0 all the way at the end. I think most of you guys did that too, right? 0 breaks down into 49 times 10 then, because of that. And then the 49 is 7 times 7, 2 and 5. So then final answer, how about 2 times 5 times 7 to the 2nd power. Yeah, perfect. That was my next comment here. Whenever we put things into prime numbers, we like very much to go from the smallest number to the larger number. So in that order, always. On the online homework, it even says, start with the lowest number first. All right, and then again, we're going to do this, the next problem here, do it by prime numbers first. Because on the online homework and the homework in the book, the numbers are so huge, you do want to break it down into prime numbers, okay? So reduce 105 over 81 to lowest terms, and I'll do the 105 first here. You want to break it down to prime numbers here. So I know 5 goes into it right away. 5 goes into 105 21 times. And 21 can still break down further into a 3 times 7 or 7 times 3. So I've broken each of these down to their prime numbers. That's what I want to do. So can you break down 81 to its prime numbers? Just putting them in order, 3, then 5, then 7. 81 breaks down into 9 times 9, of course, and that will break down into a whole bunch of 3's here. So then we say this, we say 105 over 81 really is 3 times 5 times 7 over 3 times 3 times 3 times 3. So this, in this way, we know exactly the fact that this is reduced completely. We know that there's no other way this number could be except for the 3's being canceling out, and 3 is the only number that's common to both. So 3 divided by 3 technically is a 1. The 3's can be reduced out. So on top, how about a 35 on top and a 27 on the bottom? That is the simplest or reduced form of that fraction. Again, online homework is going to go into the thousands and stuff, so you can break it down to prime numbers, you know for sure what's going to be the reduced form. Okay. And then I have this little box around it. This little box around it means on those match problems that you got, the third page usually is like an answer page. So you can technically do the match problems even before class if you wanted to. But the little box around it just means the answer in the back was wrong. So this is the correct answer. Cool. So don't look at the answer for the match problems for number 6. All right. So there it is. There's all the different types of numbers we used and the divisibility rules for those numbers. Let's jump to 1.9. And so what we have done is we've worked with fractions already. We did that on Tuesday. We did multiplication and division of fractions. That's what we did with the division of numbers. What we didn't do is just the addition and subtraction. Okay, so for addition and subtraction, there's this little word in green over here. You have to have a common denominator. And you only need a common denominator only when you're adding and subtracting. No need for common denominator otherwise. So let's do this here. I'm going to give you the problem, give you guys a minute or two, try them yourself, and then we'll check our answers as we go. So the first set. All right, let's go with this one here. So this one, notice on the bottom, all the denominators are the same. So these are already have common denominators. No need to do that, but let's just add them up. So 5/7 plus 1/7 gives us 6/7. All we do is we do the addition or subtraction. We do only with the numerators. All right, a plus 4/5 minus 2/5. How do we do this one here? Well, common denominator 5. And then we look at this little a minus, there's no a over here. So a minus nothing would still be an a over here. And then with the numbers themselves, then you go 4 minus 2 is just a 2. All right, looking at this one here, again, x is my common denominator on the bottom, and 6 minus 3 is a 3. There it is. So add or subtract only numerators here. Common denominator is 11 for D, and then let's see, 5 plus 3 is 8. 8 plus 10 is 18. No, subtraction. Okay, so it's 8 subtract 10 and minus 2. I'm trying to trick you. Good trick you. Okay, let's move on to how do we find common denominators. So I'm going to give you 2 different strategies to find them. And this one, really, if it gets really, really complicated, we use these strategies. We'll see ones that are going to be somewhat complicated. Oh, the box, what does the box mean again? Answer the match problems is wrong. Okay. So let's go with it here. Let's jump to this one right here. So we call this the LCD. We call it the least common denominator. That's what we want. We want the smallest denominator possible. So if I'm trying to find the common denominator of 5/24 and 9/16, let me give you sort of like 3 different ways to do it. We good? And this will be, you'll be able to do these. The first one is the most, if it's like humongously big numbers and you don't know what to do, you'll probably use this method here, okay? So what we do, we break down 24 into its prime factors, just like we did before. Go. I go 3 and 8. You could do 2 and 12, that's fine. Some people can do 6 and 4, that's okay too. Let's see, 24 breaks down into 3 and 8. And the 8 still breaks down into 2 times 2 times 2. And if you want to put them in order, that's fine. That's okay with me. If you don't, that's fine too. But we're going to go 16 here. 16 is 4 times 4, and each of those is going to break down into 2. So how about 2 times 2 times 2 times 2? So how do we find the common denominator? Again, this is for big, humongous problems. What we do here is we pick out any ones that are unique to each of the factors. We good? So there's only 1 3 over here. So that's going to go as a certain factor. There's 4 2's over here. There's 3 2's over here. We good? So we're going to pick the most amount of 2's. Good? So the most amount of a number of that base. So 1 3 and 4 2. So 2 times 2 times 2 times 2 times 3 would be your common denominator. Cool. Or said a different way, look at the 2's here. You only got 3 over here. You got 4 over here. You choose the highest number of 2's. Good there. There's only a 3 for the top one, so that means it's 3 to the 1. So what is that? That's going to be 48. Cool. Okay. When do we use this? Because when we have humongously big numbers. There's no way I'm going to start multiplying this number. Okay, the other common one that we normally do is this here. We do it by multiples. So 24, then we multiply 24 by 2, then we multiply by 3, by 4. So we can do this here. 24 times 2 is 48. Everybody good there? 48, so 24 times 3 would be 72. And you can keep on going forever if you like, but we usually do the first 3 or 4. Then we take a look at the next one here. 16. 16 times 2? 32 is good, yep. And then 16 times 3? 48. And once you get to the common one, you got it. There it is. There's my common denominator. Okay, we use these on smaller numbers, but numbers we can still multiply. Okay, so starting number 3 here. So I know somewhat a little boring here, but let's go for it here. So looking at 24 and 16, I would probably do this method down here for this number. I'll probably off to the side. I'll probably think about, okay, what if I multiply by 2, I get a 48. If I multiply by 3, hey, I get a 48 if I multiply 16 by 3. So then here for number 3, this is probably what I would do. I would say 48 is the common denominator here. And then what do I multiply 24 to give me 48? Technically a 2. Whatever I multiply on top, whatever I multiply at the bottom, I got to multiply on top as well. So how about 10? 16 times 3 gives me 48, and 3 times 9 gives me 27. And how about add it up to give me a 37 over 48? Good there. Usually the first method is kind of like where you start off and you're already in the hundreds. Right? You're like 135 is one denominator, and you got 128 is the other denominator. Then you're like, okay, let's break this down as opposed to multiplying. All right, so next one, number 4 and 5. Do any which way you like. Go for it. So find me the common denominator for number 4, and once you find that common denominator, use it for number 5. All right, good there. So for 21, this is what I did here. I broke down 21 7 times 3. 14 is 7 times 2. So that means I have 1, 2, 1, 3, and then they both have a 7 in common, which has just 1 7 each. So 42 is good. Or you could have done it this way here, and you could have got a 42 this way as well. Show of hands, how many did it the first way? Broke it down into its prime numbers. Cool, okay. How many did it the second way? How many didn't do it at all? Okay. At least honest, all right. Did a different way. Okay, show it to me afterwards, okay? See what you did. Okay, with this one here, so now we know that we got to multiply the 21 times 2. We got to multiply the 14 times 3. We should have got this, and final answer would be 13 over 42. All right, so next is just 2 problems here. Try yourself. Give you guys a minute. All right, let's go with it here. So 12 and 8, common denominator is? 24 is good. Multiply the 12 times 2, the 8 times 3, and we should have this, finally, as common denominators, 14 over 24, and 9 minus 24. 9 over 24. 9 over 24. Okay. 5 over 24? Okay. This one got 3 fractions at the same time here, so common denominator of 10, 3, and 4. 60 is good. Okay, so how about 3 times 20? 4 times 15, and 10 times 6. Those of you that got it, which way did you do it? Multipliers? Let's see, breaking it down to its prime factors. Cool, okay. So 60 on the bottom, I got 20 over 60. 15 over 60 is 6 over 60. And final answer, how about 41 over 60? I've seen some people say already here. Okay. And then one common thing we'll see sometimes is what happens if you're subtracting a fraction from a whole number. That's the other little piece to look at. So 4, subtract 3/4. And this one, you got students do it 2 different ways here. They can think about this here in terms of just quantities, right? Think about it in terms of $4, take away 3/4 of a dollar, you can kind of think about what's going to be left. And if you're at that stage, that's great. Now let's do the process here. So can I change any number into a fraction? Yeah, 4 over 1, perfect. Yeah, 4 over 1 minus 3 over 4. Common denominator would be? 4, so we're going to multiply the first one by 4. So that means that's going to be 16 over here. So 4 times 1 is a 4, 4 times 4 is 16. 3 stays the same. And how about 13/4? Okay, in the back of your book, it's going to usually want to write it as improper fractions like this. This is just fine, 13/4. The only time in algebra where we actually want to, bless you, where we want to get a mixed number, because we want to know the exact location of it, is when we're going to be graphing it. Whether it's graphing on a number line and graphing on an X and Y grid. That's the only time really that we going to change that into, let's see, that's going to be 3 1/4. Is that good?
Is that wrong to have that one?
No. If you have 3 1/4, perfectly fine. On the homework, when you submit it online, don't forget to put the little underscore. Right? You can put 3_1 divided by 4, and that will give you that mixed number answer. Okay, and the last problem here, this whole concept of sequence. Can you recognize a sequence? Now this one doesn't tell you here. This could either be a multiplier or this could be an addition. But it all has to do with fractions here. So let's maybe do the first one together. I'll give you guys the next two to do by yourself, just sort of think about it. So 1/5. Something happens to that, it becomes a 0. And then something happens to that, it becomes a -2/5. Especially with a 0 in there, you can't be a multiplier anymore, right? Because 0 times anything is still going to be 0, right, from then on out. So it has to be an addition or a subtraction. In this case, if you agree here, 2/5 subtract 2/5 would give you the 0. And 0 subtract 2/5 would get you to a -2/5, right? We're subtracting 2/5 each time. That's kind of what we're doing. There's your pattern. So now the question is, what is -2/5 subtract another 2/5? The little trick here with fractions here. Remember how we don't like really subtracting numbers here? We're going to change this to addition problem, and we're going to take the opposite of our numerator. We're good. Does that seem to be a lot easier to do? So whenever we have subtraction, what we're going to do is we're going to change it to addition, and we're going to take the opposite, just like we do with integers. Cool. So how about -4/5? Is that good? That's our final answer? Okay, see about 3 blank stares at the screen here. I think you just saw a ghost, so talk to me. No, don't want to talk to me, okay. Alright, B and C, all yours. Give you guys a minute, try it yourself here, see if you can figure out what the pattern is, and from there give me the next number in the sequence. Let's go for it, let's try this together. So 2/3 now becomes 4/3. Adding 2/3, would that work? Because if you have the same denominator, then the question is, what are you adding to from 2 to get you a 4? Hey, 2. Awesome. Okay, then this weird thing. How come it turns into a 2? Let's see. 4/3 plus 2/3 would make 6/3. That's right, huh? 6/3 is really technically a 2. Okay, cool. So then 4/3 plus 2/3, there it is. It's 6/3, and 6/3 technically a 2. So then from here, I got 2/1 plus 2/3. Common denominator has to be a 3. Are we okay there? 6/3 plus 2/3 give you 8/3 as your next term in the sequence. Alright, and the question usually comes up, Mr. H, these are kind of weird. That's okay. They're not going to be on the test, so we're good. Cool. Okay. These number sequences are not there, but they really just forces you to think a little bit more deeply into numbers here. Okay, so 1/5 goes into a 1/10, goes into a 1/20th. Notice the denominator is changing very rapidly. I want to say it's probably a multiplier. So 1/5 times 1/2, would that make you a 1/10? I think so, right? 1 times 1 is still a 1. 5 times 2 is 10. And then 1 times 1 is still 1, and then 10 times 2 is a 20. So now the question is, what is... Perfect by me, yep. 120 times 1/2 gets you 140. Okay, kind of quick show of hands here. 3 different options here. chapter 1 was the easiest thing that I've ever done in my whole entire life. Okay? Or chapter 1 was, Mr. H, it was actually pretty easy for the most part. I didn't have any hang-ups. Or third option is, Mr. H, this was kind of weird. It was kind of difficult. Besides the sequence problems, okay? So raise your hand. Chapter 1 was like, this was so freaking easy. I could die and still do it. Okay. Mr. H, chapter 1, little tiny bit of a challenge, but for the most part it was okay. Okay, and then, yeah, and then it was weird stuff here, Mr. H. This was nothing I've seen in pre-algebra. Okay. Okay. Just to give you sort of perspective here. So chapter 1 should be pretty easy. Should we answer the first two? If you answer the third one, probably maybe tutoring. Probably a lot of extra help. Stay after especially if you need to. All that good stuff, okay? All right, let me do this here.